Hello, I'm Alex Howe, and this is the Science Meets Fiction Exoplanets review for September of 2022. Now, to start off, there are always plenty of new planet discoveries to go around, but in September there was one pretty major new planet discovery, described by this paper, 2 temperate super-Earths transiting a nearby late M dwarf. So this is a planet that will probably look quite a bit like this, except there's 2 of them. This star is known as LP 890-9, or as TOI 4306, or as Speculoos 2. We really need a more standardized catalog of these things. Anyway, this is a very low-mass red dwarf, only 12% the mass of our Sun. You can compare that with the infamous TRAPPIST-1, which is 9% the mass of our Sun. It has 2 super-Earth planets, one of which is probably more Venus-like, but the other, Planet C, which is a rocky super-Earth, we're pretty sure, is expected to have a temperature about the same as Earth. So that's already a pretty big deal. And it's worth noting that these planets are orbiting one of the smallest red dwarf stars that is known to have planets. In fact, according to this, the smallest, except for TRAPPIST-1. And they're transiting planets, so we can measure the composition of their atmospheres by the spectra of starlight passing through them, and those transit signals are expected to be the highest for any planets in the habitable zone, except for the TRAPPIST-1 planets. And this is a very big deal. It didn't get as much media attention as TRAPPIST-1 with its 7 planets did, but it got a fair bit. And with a super-Earth in the liquid water zone, around such a small star with such a large transit signal, that's a big deal. I wasn't even sure that we would get any more transiting planets that were such good candidates for spectral characterization. So I expect this planet to be a top priority for Cycle 2 on JWST next year. However, I said this was a potentially habitable planet, but there's one caveat to that. In this follow-up paper, Hot Earth or Young Venus, Lisa Kaltenegger and her group reconsidered what the climate on this planet would be like. LP 890-9c receives 10% less sunlight than Earth, which you would think would give it a pretty comfortable temperature. But the thing is, especially for red dwarf planets, we are not actually sure where the habitable zone is. The greenhouse effect can do weird things, and even for 10% less sunlight than Earth, water loss and a runaway greenhouse are very real failure modes in our climate modeling. So we have to consider the possibility that this planet is Earth-like, or has a CO2 greenhouse like Venus, or has a steam atmosphere and a water vapor greenhouse, which is what we think happened on early Venus. But of course the water's all gone today. And they made predictions of what the spectra will look like. And it's fairly obvious. This is covering the entire JWST range. With a steam atmosphere, you just get these nice, neat water bands. With a CO2 atmosphere, you get the narrower CO2 bands. And then, of course, with an Earth-like atmosphere, you get this complex spectrum, because there are more different trace gases that are of interest. Now, that was the most important discovery from September, but there were others, and I thought this one was especially interesting. HD 23472, a multiplanetary system with 3 super-Earths and 2 potential super-Mercuries. This is TOI 174, if you're keeping score. And this team followed up on the TESS transit observations with the espresso spectrograph doing radial velocity measurements to measure the masses of these planets. And this is an orange dwarf star, so it'll probably look more like this, although all of its planets are hotter than Earth, so they probably won't look blue, although there are some conditions where the atmosphere could be blue. But the important thing is where they fall on the mass radius diagram. And you can see we've got 2 planets up near the top, with radii larger than 1.8 Earth radii, which is above the radius gap, suggesting they are mini-Neptunes with a hydrogen atmosphere or at least a large water content. Another one that's closer to Earth size, but is still fairly low density. It's not clear what's going on there, although it could just be the error bars. And then we have two that are down near the bottom, which seem to be quite clearly denser than Earth. And this makes them part of a growing, although I may add disputed, population of super-Mercuries that are presumed to be iron-rich, like Mercury, which is 70% iron, and much denser than most super-Earth planets, even the solid ones that are majority rock with no hydrogen. And I've talked about this in previous reviews. We're still trying to figure out how these very iron-rich planets form. And perhaps as we observe more of them, we'll get a clearer picture of where and how they occur. Some work that was done to characterize planet populations last month. Of course, the ultimate goal of measuring the demographics of exoplanets, other than just the general science, is to figure out how many of them could be habitable. And there was a major paper updating our estimates of that, the demographics of Kepler's Earths and super-Earths into the habitable zone. And this is based on what by now is some older data from the Kepler Space Telescope. The mission goal of Kepler was to find Earth-analog planets, by which I mean Earth-mass planets in the liquid water zone around a sun-like star. And we found quite a few planets that meet two of those criteria, but not all three. Kepler didn't quite get there because of two problems. One was that the reaction wheels failed, so the main mission was cut short. It met the design goal of 4 years, but that turned out not to be enough because of the second problem, which is that most stars are more active than our sun, and that creates noise in looking at transit light curves. And that is something we just didn't expect and couldn't really anticipate. And it's possible there was some bad luck, that there just weren't any Earth analogs in the sample. In any case, given the observations we do have, we have to extrapolate and estimate what the numbers look like in the habitable zone of sun-like stars. And that's exactly what this team did, and they estimated that 15% of sun-like stars will have planets that meet the definition of Earth analogs. And perhaps twice as many have sub-Neptunes. The sub-Neptunes do seem to be the most common type of planet in the galaxy, as far as we've been able to measure. And they did something fairly innovative by breaking down the quote-unquote sun-like stars, which are really F, G, and K type stars, into 5 mass bins, and they're still all kind of clustered around 15%. If you look at the second line in this plot, those are the error bars on their overall estimate, and they are smaller than previous estimates from the past few years. And I'll note that the vertical gray line is the occurrence rate that has been assumed for future mission planning, and that's important because this paper, and actually several of the papers from the past few years, suggest we may need to revise that down, and future planet hunting missions may be a little more difficult than we thought. There was also some interesting new work for longer period planets. Joint constraints on exoplanetary orbits from Gaia DR3 and Doppler data. And this is an emerging area of study made possible by the most recent data release from the Gaia spacecraft. This is by Josh Wynn at Princeton, and my colleague Tim Brandt and his team at Santa Barbara have been doing the same thing with brown dwarfs. And this is a really cool idea because we can now get 3D motions of stars, which reflect the gravitational influence of their planets in all directions and not just along the line of sight. This allows us to get edge-on and face-on systems equally by combining the astrometric measurements of positions in the sky from Gaia with radial velocities, which tell us motion along the line of sight. And here's an example of those data. On the left, you can see a radial velocity curve, and on the right, you can see the motion of the star on the plane of the sky, and together that gives us a 3D picture of the star's motion, and of course the planet moves opposite to that. And in this paper, Josh Wynn detailed 5 Jupiter or super-Jupiter type planets with periods of 1 to 4 years. There's another type of long-term trend that we're looking out for, and that is orbital decay. This is evidence of long-term period variations in the exoplanet transit database, And this title's a little unclear. At first, I thought it meant looking for transit timing variations that indicate a more distant planet. With a longer and longer baseline of many years, you can detect long-period planets, and we've done that in some cases. More often for radial velocities, but the idea is the same. But this is looking at orbital decay. So hot Jupiters that orbit very close to their stars will experience orbital decay due to tidal forces dissipating energy away from its orbit. We've found one example, which is WASP-12b, which has a measurable decrease in its orbital period, which predicts that it will collide with its star in a surprisingly short time of only 3 million years or so. And that's fine, because with the number of hot Jupiters we've seen, there's room for one or two statistical outliers like that. And here's the transit timing plot for WASP-12b, showing how far the transit drifted in time over many years. That's days along the x-axis. But if there's one WASP-12b, there should be several hot Jupiters with somewhat slower orbital decay that are not quite as close to colliding with their stars. And this group led a citizen science project to look for orbital decay in a transit timing database for other hot Jupiters, and they found 8 candidates so far, with many more left to analyze. And here's one example, TRES-2b, and I just picked that one because it's well known for being one of the darkest planets we've ever found. Reflects very little starlight. And it does appear to have a slight orbital decay. It's not as conclusive, and it's several times smaller than WASP-12b, but it does seem to be there. So that's an exciting ongoing development, and in a couple more years we may have some good population statistics on orbital decay. So keep an eye out for that. I saw some interesting papers last month about planetary systems and how they evolve over time. The first one here is tidally induced migration of test gas giants orbiting M-dwarfs. And this is based on the fact that gas giants around M-dwarfs are kind of hard to explain. As I've said in past reviews, we expect small stars to have small planets. It's unusual, or should be unusual, to find gas giants around M-dwarfs, especially close in. If they're farther out, where there are more solids, more ices to form larger planets, that's more understandable, but it's really hard to explain them if they're close to the star. And what Jamie Alvarado Montes did was model the tidal migration of gas giants around M-dwarfs. And usually planetary migration is associated with planet formation. Either it's due to interactions with the protoplanetary disk, or it's interactions with another planet, which, just because of how chaotic systems work, is still likely to happen fairly early in the history of the solar system. But tidal migration can go on for a long time, just like our moon has been migrating away from Earth for billions of years. And for M-dwarf planets, we see kind of similar results. Gas giants, this is just one example, can migrate inward towards an M-dwarf for billions of years before colliding with it. And this is down to things like the rotation period of the M-dwarf, and how fast its rotation slows, and the exact makeup of the planet. But it appears that we do need to consider tidal interactions over billions of years when modeling how exoplanetary systems are structured. And another one, although this is more back to formation, has to do with looking at the orbital resonances of planets. So some exoplanets we see are in orbital resonance with one another, where one planet will orbit 3 times in the time it takes the next planet out to orbit twice. And we see orbital resonances in our solar system with the moons of Jupiter. But while there are some resonant exoplanets, most of them tend to pile up just outside the orbital resonance, slightly farther apart. And that's been a big mystery, because we expected them to be right on the resonance. We have a couple examples from our solar system of 3-2 resonances, Pluto and the other Plutinos in the Kuiper Belt with Neptune, the Hilda asteroids with Jupiter, and those are right on the resonance. So the fact that the planets aren't is surprising. And this paper tried to explain that by gravitational interactions with the planetesimal disk. Not the gas disk, but the disk of solid bodies that is left behind during planet formation. And the details of the interaction are complicated, but the bottom line is gravitational interactions with the planetesimal disk tend to make planets preferentially drift apart from one another. So they could be non-resonant to start with and still move slightly farther apart in orbital distance, or they could be resonant to start with, which we think is a common formation process, but be pushed out of the resonance to just outside it. So that would be a pretty important piece of the puzzle of planet formation if we can confirm it. And there was a lot of interesting new work on planetary atmospheres last month, in various aspects. This first paper here, this is one of those ideas in science that seems obvious yet profound at the same time. Density, not radius, separates rocky and water-rich small planets orbiting M-dwarf stars. And in one sense, this is trivial. Density is literally the thing that characterizes what a planet is made of. Radius is just a useful proxy for density since we don't always have good mass measurements, and we've suspected the whole time that it's not exact. But there hasn't been that much work looking at density directly. And this paper does that. So here on the left, there's a sampling of planets on the mass radius diagram, with tracks for 50% water composition and Earth-like composition. And you can kind of see there are a lot of planets that lie along the two lines, but also quite a few others, including the ones in gray, that are not on the lines. And it's not really clear where to draw the populations. But since they have masses and radii, that means we do have densities for these planets. And if you plot mass versus density, you can see two populations much more clearly. There's one population that's very clearly clustered around the Earth-like composition line, and another that's clearly clustered around the water-rich line. Now, we don't know for sure that they are water-rich. This is one of those ongoing problems. It's hard to tell if these planets are 50% water or 1% hydrogen. The authors of this paper assert that they're mostly water-rich. And you can kind of tell because if you look at a water-rich track and a hydrogen-rich track on the mass radius diagram, a lot of these planets fall along the water-rich track. And only the ones that are above it are the ones that we can confidently describe as hydrogen-rich. Now, I wasn't entirely convinced of that because of the variables involved, but they got a very interesting result when they plotted a histogram in density versus radius. You can kind of see the different populations of planets at different radii, and there are some outliers, but you can kind of see the radius valley in there. But if you plot a histogram in density on the left, you get a much sharper distinction with three distinct populations: rocky, water-rich, and hydrogen-rich subneptunes. So the claim here is that for planets with good enough mass measurements, it's much easier to see the separate populations in density. And again, this is unsurprising when you think about it, because different compositions have different densities. But it is surprising because we haven't had data that are good enough to make it this clear before. And again, I think this is very interesting because the initial discovery of the radius valley suggested that there were very few water worlds, because their density should be intermediate in the radius valley. But here it looks like there are probably a fair number. And that's actually better for formation models, but still leaves a few problems left to be solved. Now, speaking of water worlds, this paper is called Life on Exoplanets in the Habitable Zone of M-dwarfs, but it's actually about water on M-dwarfs. And the reasoning here is that M-dwarfs, that is red dwarfs, have several problems for hosting habitable planets. They produce a lot of UV flux, which can strip away the atmosphere. They evolve slowly, so they are too hot when they're young. Planets in the habitable zone will be tidally locked, which may or may not cause problems for life. But this team raises one more consideration, which is the need for an asteroid belt. Or more precisely, the need for large numbers of asteroids that can deliver water to the planet from outside the snow line. We think that most of Earth's water came from the outer solar system where ice can form. And we think that gas giants like Jupiter are needed to form an asteroid belt and keep the material in that region from just coalescing into another planet. And as I said before, gas giants are less common around M-dwarfs. Or are they? This team looked at the gas giant population around observed sun-like stars and M-dwarfs, and while hot Jupiters are much more common around sun-like stars, M-dwarfs have quite a few gas giants in Jupiter-like orbits. So that suggests that they could form asteroid belts that would deliver water to their inner planets. So that obstacle appears not to be an issue. But I thought this was especially interesting because there was another paper that suggested it might not be a problem at all because M-dwarfs could have another source of water. And again, this is down to formation models and the difficulty with how water is handled in them. Depending on which models you run, you can predict that M-dwarf planets have no water or much more water than Earth, which is its own problem because if the ocean floor is buried under layers of high-pressure ice, that's going to make it harder for life to get started. And to address this, this team used an improved model of planet formation that doesn't just deliver water from the outer system, but also adds chemical interactions. Especially in a high UV environment, the primordial hydrogen atmosphere, which all planets will have even if they lose it, can interact with oxygen-rich silicate minerals to produce water. So this would be another source of water that doesn't have to be delivered by impacts. And you can see two of their models, with and without this chemical enrichment process, compared with older population synthesis models, showing the logarithmic water content of terrestrial planets. And the single bar on the left is planets with no water, and on the right are water worlds. The gray line in the middle is Earth's amount of water content. And even their unenriched model had a wider distribution than older models, but their model with this chemical enrichment produces M-dwarf planets with a wide range of water content, from 10 times less than Earth all the way up to water worlds, and everything in between. So this is another reason to think that we could have a wide diversity of water content on these M-dwarf planets. There were also a couple of interesting papers about atmosphere loss. This first one looks at the effect of stellar activity, which is something I've talked about before. Photoevaporation, we think, is one of the major processes for mass loss from exoplanets, where, again, high UV and X-ray emissions from the star can strip away the atmosphere. But this paper looks at the fact that stars of the same mass and age may still produce very different amounts of UV. Just like I said earlier about how our sun is quieter than the average star. And they modeled what effect these different levels of UV radiation would do to exoplanets. And we usually assume it's the first 100 million years of the star's history that is the bulk of the mass loss, but this paper found that it can be as long as 500 million years before things really settle. So they looked at different UV radiation histories, and this is specifically for sun-like stars, and of course this is from a 2012 paper. And the usual model is that a star's UV output will stay steady for a while, about 100 million years, although it can vary quite a bit, and then drop exponentially. But you can see in this figure, there's a lot of variation there. And if you compare photoevaporation from low, medium, and high UV stars, you can get different planet populations. So this is the planet population over radius, and you can see the dip in the middle, which is the radius valley. But for high UV activity, you get a lot more super-Earths, and the radius valley occurs at a larger radius. Whereas for low UV activity, it's not as dramatic a change, but you get slightly more mini-Neptunes. And they also looked at the effect with time and specific star clusters, and you can see the evolution of the population. This is for an average UV exposure, from a young age of 60 million years to 5 billion years, and you can see the number of super-Earths increases, the number of mini-Neptunes decreases, and the radius valley moves to slightly larger radii. So that's something to keep an eye out for if we can get good measurements of planets and clusters. And finally, we have this paper putting together two bits of physics that we consider in planet formation and evolution, but not necessarily how they interact with each other. And this is mass loss and radioactive heating. So on Earth, about 2/3 of the geothermal heat coming from the ground comes from radioactive decay of primordial isotopes that have just been there since the beginning. And that's probably even more important on super-Earths because they have a higher mass-to-surface area ratio. So they stay hot longer. The thing is, uranium and thorium will sink to the core, but potassium hangs around in the mantle. It binds to rock instead of iron. And when the planet is forming, it's likely to have a magma ocean on its surface, and potassium-40 can be outgassed from the magma ocean into the atmosphere where it can then be lost to space. And of course, that will decrease the geothermal budget of the planet going forward, which will significantly impact its geological history. And these are preliminary results still, but you can get an idea of them from this plot, which is the ratio of potassium abundance in the planet with to without mass loss. And you can see in some of these models, almost all of the potassium is lost. So that could be a major decrease to the planet's radiogenic heating. So I think this work is still ongoing, but I'll be interested to see where they take this.